Hey students, in this section we're going to talk about end effectors or end of arm tooling. So we're going to talk about how do you take a robot, just a standard robot that you get, and adapt it to the process that you are making. So this turns out to be quite a challenge in a number of ways. So let's look at those ways that this is a challenge. So first of all, robots have many degrees of freedom, and they have a long range of motion. And because of that, end effectors must have ways to accommodate any positional inaccuracies. So because they can move in so many different directions and because they have such a long reach, they tend to not be very rigid. When they're out there at full extension, they bob up and down. And when you're trying to position parts into fixtures within thousandths of an inch, or do machining to tenths of an inch, a robot that is flopping around at quite a bit more than that really has quite an effect on what you're doing. And so both the end effector and the fixture must be able to accommodate some out of position tolerance of the robot, and then work to put the part into the right position or to grab the part even though the robot's not quite in the right location. Now you'll get numbers from the robot manufacturers that are much better than this, but you have to remember that that's before you've added end of arm tooling on there, the weight of the end of arm tooling, and before you've cranked it up to a speed where you're actually making money. So in a very slow motion, yes, they can position to a thousandth of an inch or maybe even less, but when you're actually moving at the speed that you need to do to make money, and you have a heavy end effector on there, that's going to be difficult. Speaking of heavy end effectors, robots have really limited load capacity. It's surprising how limited they are, and it's because of the stiffness of that arm is really hard to achieve, and so they are not able to lift very much. If you put bigger load capacity, then you have to pick bigger motors. Motors weigh a lot, and so then the whole robot has to get bigger. All of the parts of the robot that are supporting the motors that are further and further out on the arm have to get bigger. So that's a challenge. So one of the big things that we try to do is in our end effectors try to really reduce the mass. So this is a big difference from the way that we do our fixtures, right? Because we take our fixture generally, if it's a machining process or even a gauging process, and we try to make it really robust, and if it weighs a little bit more, it doesn't matter that much. But on an end effector, that is a non-starter. Robots have non-orthogonal axes in general. Not 100% true, but most robots have non-orthogonal axes, and so they approach in non-orthogonal directions. Often they're approaching in a somewhat rotary direction or a combination of rotational directions at the same time. So again, the end effector and the fixture have to do some assistance with location, just because the motion is not easy to do directly and straight into the fixture. For instance, one of the things that happens is you would like to have the part come in, position above the fixture and lower straight down into it. And if you're in the middle of the robot's reach, it can do that. It can move straight down. But remember, for it to move straight down, it has a bunch of rotary axes. Then it is having to run those all at the same time to try to interpolate straight down. So that will take the robot running 3, 4, 5 axes all at the same time. If you're out near the end of its reach, it just can't do it at all. It only comes down in an arc. And because it comes down in an arc, you have to make your fixture so that as the part comes into it on an arc, it will nestle the part into the right place. And then when the robot comes to pick it up, you have to have enough tolerance in your fixture that it allows the robot arm to arc in there. Robots run for many shifts. The point of having the robot there is that the robot doesn't take a break and the robot doesn't get a break. And so end effectors have to be very durable, and they need to be very easy to work on. They're always going to break on third shift in the middle of the night, and so you need it to be something that can be lots of easily replaceable parts and just very clear what's going on, very simple and well designed. So that is really important. Need biposition actuators is a really good advance. A lot of times, or it's a necessity, a lot of actuators can only open or close, or they just move. You know, it's just a cylinder and it moves, extends and it retracts. It extends, it retracts. And so that's very common on robots, on their end effectors, that you have the simplest kinds of motion. So you can put servo motors where you're controlling all of the axes at the same time, and that has gotten a little bit easier as microelectronics have gotten smaller, but that doesn't make a very durable, very robust end effector. So a lot of the times the end effector is just, you know, extend the piston, retract the piston. And so to be able to deal with that, you have to be able to confirm the part pick and the part placement. You have to take that single direction of motion and make it into multiple directions of motion, whatever direction you need. And then you have to balance between gripping force and a range of motion. To show you what I mean by that, here are some standard gripper designs. And so you can see that each of these takes motion in one direction. So here it's motion moving these two arms closer to each other, so you could think of a piston tied to these two, and as you actuate it, the piston retracts and they move together, and then these arms over here move together as well. And the ratio of this short arm to the longer arm will say whether if this arm is shorter, then the motion out here is amplified. If this arm is longer on this side of the piston, then the force is amplified out here. And so you can either amplify force or motion, length of motion, but you cannot amplify both. One thing that you'll notice about this is while this shows the force happening in an axis perpendicular to the arm, which is true, the motion of this arm of these locators is going to be in an arc. And so if your part is large, like this, then the part is not going to be clamped with vertical force on it. It's going to be clamped with force that is coming in along that arc. And because of that, there will be some amount of the force that wants to squirt your part out of the grippers. And so you can see in this design they put V's in the grippers so that to counteract that force trying to squirt the part out. Some other designs here, you can see this one takes a horizontal motion of a single point, so that's a little bit easier than moving 2 points at the same time. So just moving 1 point, and that makes these two close. Now if the part is close to this size, then the force is nearly orthogonal to the axis of motion, and it would be normal to the surface of the part. But if the part is small, you can see that if the arms were down here grabbing a small part, then the force would be inward. And sometimes that's great because you can put a stop right back here. I don't know exactly, I don't know exactly how to draw a stop back here, but let's just say that that is a stop right back there. And so then the part would sort of be gathered by these two and the force would push it into the stop. And so that would help you to grab it. Here's another that is a similar design to this one, except that the amplification of the force is different. So as you move this out, you can see that you're taking a small motion in here and amplifying it to a very large motion. That means that the amount of force will be quite a bit smaller out here. The other thing that you can see is that these are coming with a non-orthogonal force direction, and so especially if it is a big part, it is going to have some component of the force. Wow, that's a nice arrow. Some component of the force there again that is trying to push the part out, and so you have to be aware of that. Here's another kind of pincer. Move it this way. This one will amplify the quantity of the force. So you have to move this a long way. These grippers will collapse a shorter amount, but they will amplify the force and hold the part with a greater force. So let's talk about some best design practices when you are creating some fixtures. So first, use sensors to determine part pickup and drop off and whether you did achieve the part. Generally, it is great to use the most simple sensor that you can. So those might be proximity switches that are just looking for the presence of a piece of metal at a certain location, or it might be a limit switch, which is just gets hit by the part or by the arm just to confirm that something is there. So one way to do this, if we count the blue as a fixed arm and then the black as a sliding arm, and it slides side to side, and we want to catch this egg here, one thing you can do is have a little bump on the side of the sliding arm. So this would just be a little metallic bump, and here are 3 proximity switches. And so proximity switches work on inductance when they are in the presence of metal. It will change the impedance in their circuit, and that impedance change will notify them that there is something clear or something present. It's the same way that the sensors work at traffic lights. So your car comes into a loop, it changes the impedance, the presence of the metal, or your bicycle changes the impedance in the loop, and that tells the traffic light that there is somebody there waiting and that the light needs to change. A lot of people think that it is weight, but it is not by weight, it is by impedance. Okay, so we have this sliding arm, and you can see that if it has the little bump in line with sensor number 1, that tells the robot that the arm is open. And then as you try to grab the part, this arm slides in, and if it grabs the part, the sensor will stop with the bump next to sensor number 2, and that will be great. The robot will know, okay, I now have a part, and if you commanded it to grip and it did not make it there, it means that your egg is in sideways or something else is wrong and it needs attention and help. Then also with the same system, if you happen to not pick up the egg, or if the egg falls out, then the sliding arm will continue to slide forward. So you'd have something like compressed air on the back of this pushing the sliding arm in. And near the end of its range, it would put the bump by sensor number 3, and that would tell the system that there is no part present. Even though you commanded the gripper to close on a part, there is no part present. So this is a really simple system. These sensors are not very expensive. They are incredibly robust. They're robust to coolant and getting hit by things. They sit down mostly protected inside, something like the fixed arm here. All it takes is a piece of metal sliding by them. They're pretty robust with chips and all kinds of other things around. They just they can be tuned to only see this kind of amount of metal and at the right distance, and besides that they'll sort of not react to them. So anyway, this kind of foolproofing or just checking to make sure of what you've done is really important. You can also do this with cameras now. So you can have a camera there that looks to see if the part is in there. But that's a whole lot of processing power and hundreds of dollars of camera equipment and lighting and lenses, and then you have to have a processing system that doesn't get fooled when the sunlight comes in the side window and lights up the table. Just all kinds of things. This is 3 simple sensors, and so something like this, a method, it doesn't have to be a sliding arm, it can be a swinging arm. You can think of how you would do that on a lot of these. You could just have the sensors at different locations around the arc. So if the arm is in front of the sensor, it would tell you exactly the same information that we're learning here. And then an important idea is to provide stops in the gripper's travel to prevent end of travel motion. So you don't want this little bump to smack into this area because it might ruin the bearings that are allowing the arm to slide. And so putting in a stop that will prevent that from happening is really important. On all of those previous designs, you would need to have a stop somewhere that prevented the, if you are using a piston, the piston from going against the end of its stroke, which will damage the piston. And then you want to minimize the number of power sources on the robot, because all of these have to be taken all the way up the robot, all the way around all of the joints in the robot. At every joint they have to have a bunch of extra length, and that extra length can get caught on things, plus it's extra weight and resistance to motion that the robot has to overcome. And so in a fixture, as much as you can, choose 1 or 2 types of power source and stay with them. So if you want to use air and create suction with that air, that's great, do that. If you're doing that, instead of using electrical switches like this, they make switches like this that are air pressure switches. And so if this slides over the end of the sensor, it will create enough pressure in that line that then a switch somewhere back further up the robot would be triggered, and you would know that you had what you needed. Or you can use air and electricity so that you could have them out there, but just try to minimize the number of power sources that have to be carried out to the end of the robot. And then finally, robots are a huge balance. And so it's a balance between determinism, which you would love to have, because you're picking up a part, you're putting it in a location, and you would love to have a lot of determinism in how you pick it and how you place it. On the other hand, you don't want to just barely grab a part, because then you'll have to move the robot so slowly to keep from flinging the part across the room or dropping the part that you won't make any money. So there is a need for stability as well. Need durability in what you're doing. So while determinism would say let's have the smallest contact areas we can, durability is going to say, well, let's make those contact areas pretty good size so that they spread the load and they really don't wear out very quickly. And then cost is a huge issue to try to overcome. Anybody can design a gripper that is worth a huge amount of money, but designing a gripper that is really elegant and solves the problem simply and inexpensively is really good design practice. All right, I'll see you in the next video. We're going to look at a bunch of different examples and try to draw some ideas of what makes good end of arm tooling designs.